In our project, we're tackling the challenge of simulating the structural coloration of butterfly wings. Unlike traditional pigment-based colors, butterfly wings are iridescent and not one, but rather many different colors, depending on the light position and the viewer's position. Iridescence is an optical effect in which the color of an object appears to shift depending on that viewing angle, because of the way the light refracts and reflects off the object's nanostructures.
Traditional rendering methods that use simple RGB systems fail to capture the complex optical phenomenon of iridescence. In standard RGB rendering, colors are represented as fixed combinations of red, green, and blue values, but iridescent materials like butterfly wings don't have a single color. Instead, their appearance depends on complex wavelength-dependent interference patterns dependent on the viewing angle. This means that for any given angle, certain wavelengths constructively interfere, while others destructively interfere, creating a dynamic spectral distribution that RGB rendering cannot accurately represent. Spectral rendering, which simulates light transport at multiple wavelengths across the visible spectrum, is theoretically necessary to properly model these interference effects. In our project, we achieve a balance between physical accuracy and computational efficiency by incorporating spectral considerations into an RGB rendering framework.
We have currently implemented a multilayer interference BSDF class in our existing Homework 3 ray tracer, which is inspired by the work of Yinlong Sun in their paper from 2006, which we cite in our report. This BSDF calculates the object's reflected radiance at a point dependent on the ray's accumulated phase shifts and its interference based on how the ray travels across multiple thin, transparent layers. The empirical reflectance function that we make uses a phase term that depends on the film thickness, refractive indices, and incident angles.
To test our BSDF, we generated some Collada files using Blender. Initially, we encountered some file compatibility issues, but we were able to resolve them by examining the differences between the old working files from Homework 3 and our files that weren't working and adjusting our structure accordingly.
As seen in these rendered images, different colors form as a function of the viewing angle relative to the light source. These images test our BSDF using a simple sphere and point light. We've also explored how varying the interference power parameter M affects color formation. As shown in the image, when the parameter is small, shown on the left, the colors appear broad and mixed. And as it increases, moving towards to the right of the image, the colors become more saturated and sharply defined.
In the coming weeks, we plan to expand our code to include more complex geometries like butterfly wings and beetles. We want to enhance our lighting setup by having multiple light sources instead of just a single point light to better highlight the iridescent effects. And we plan to improve our spectral sampling beyond the current RGB approach.